In today's video, we're going to be talking about the speed of sound. And after watching this video, you should be able to determine the speed of a sound wave, understand this thing called the Doppler shift, and then be able to do some conceptual Doppler shift problems. You won't have to mathematically figure out any Doppler shift problems, but conceptually you should be able to understand what happens to a sound wave when an object or the sound is moving to or from a point. And we'll talk about that a little bit later. So let's get right to it. First, we want to talk about wave speed. The speed of a wave is dependent upon the medium which it travels through. Okay, so sound waves have a different speed when they travel through water than, say, compared to air. They also have a different speed when they travel through, say, like steel than compared to air. And it's kind of weird, but sound waves actually travel fastest in solids, then they travel next fastest in liquids, and then they travel the slowest in gases, which to me it doesn't make the most sense, but that's actually the case. So that the speed of those waves is dependent upon the medium which it travels through, whether it be air, water, steel, whatever the case may be. The speed of a wave is defined as the distance that a point on a wave, such as a compression or a rarefaction, travels per unit of time. Okay, so that hasn't changed since first semester physics. And the equation for speed also has not changed, where basically speed is distance divided by time. Okay? Or, now that we're dealing with waves and sound waves, we can use another formula called where it's speed equals the wavelength, which is typically represented by lambda, times the frequency, which frequently will be represented by the hertz. Okay? So this is another formula you can use to calculate the speed of a wave. And again, I know I keep hammering this over the head, but remember, this is an important point. The speed of a wave is dependent upon the medium in which it travels through. Okay, so these factors will be adjusted based upon that medium. So let's do an example problem to kind of maybe help get this idea across. Let me just change to, we'll go with yellow today. It says an automatic focus camera is able to focus on objects by use of an ultrasonic sound wave. The camera sends out a sound wave that reflects off a distant object and returns to the camera. A sensor detects the time it takes for the waves to return and then determines the distance an object is from the camera. If a sound wave has a speed of 340 meters per second and returns to the camera in 0.15 seconds after leaving the camera, how far away is the object? Okay. As always, with these types of problems, I really recommend drawing a diagram. So if I draw a little camera here, and let's say the object is here, basically what it's doing is it's sending out a sound wave, or ultrasonic wave, hits the object, and then the ultrasonic wave kind of comes back to the camera. And by using basically the formulas that we just talked about, the camera is able to figure out how far away the object is so that it can focus on it and take a good picture. Okay, so this is the same idea of like what bats use to basically fly around and not run into things. Okay, so I am thinking, one, that this distance here, d, is going to be important. I also am thinking that this information that they give us here, that the speed of sound is 340 meters per second, is also going to be important. So I'm going to write that down here. The speed equals 340 meters per second. Okay. The time, I also think, we're probably going to be an important piece. The time is 0.15 seconds. Okay. Now, here's the trick to solving this problem. I'm assuming we're going to use speed equals distance divided by time to solve this. And some of you may want to just start plugging things in, because we know the speed is 340 meters per second. We know the time is 0.15 seconds. But the trick to this problem is you need to realize that that time was for basically this wave to travel from the camera to the object bounce off the object, and then head back to the camera. And it took 0.15 seconds. I don't want to know that whole distance, that whole pathing that it took. I want to know just d. I don't want to know, for instance, 2d, okay, because 2d is going there and back. I just want to know d. And so this time, I actually have to cut in half. So half of 0.15, if my math is right, is actually, or let me write this out. So times 1/2 equals 0.075 seconds. Okay, so half of 0.15 seconds is 0.075 seconds. Now that I know that new time, because that's the time it takes basically for this wave to travel from the camera to the object, I can now plug this into my formula, and basically to get distance, it's going to be d equals s times t, or speed times time. Okay, so what is 340 meters per second times 0.075 seconds? Well, that answer is 25.5 meters. And that's how far away this object is from the camera. Okay. Let's do one more problem where we use the other speed formula. It says, on a hot summer day, a pesky little mosquito produced its warning sounds near your ear. The sound is produced by the beating of its wings at a rate of 600 wing beats per second. What is the frequency in hertz of the sound wave? Okay, remember, frequency is basically, if you will, beats per second, or beats per second. So the frequency actually is given to us almost right off the bat. You just have to recognize that this number is the frequency. And so our frequency is 600 hertz. Once we know that, we can then use the other formula that we talked about, which basically says that speed equals wavelength times frequency. Okay, so I know that one, the frequency is 600 hertz, and the speed is given to us as 350 meters per second. So this is assuming the sound wave moves with a velocity of 350 meters per second. What is the wavelength of the wave? And so I'm going to write 350 meters per second here equals lambda times this. Okay, and then you just got to get lambda by itself. And if you do that, basically just do some math, 350 divided by 600, you would find a wavelength of 0.58 meters. Okay. So that's basically the types of speed wave of sound wave problems I could throw at you. So if you can do those, you'll be sitting pretty. So the next thing I want to talk about is this thing called the Doppler effect. And the Doppler effect is basically something that happens to sound where it's this change in frequency, or the change in the pitch, either gets higher or lower sounding, is caused due to the relative velocity between an observer and the sound source itself. Okay? So I have some pictures that will kind of help explain this a little better than maybe that sentence will. When the object approaches the sound source, so let's say you have a sound source that's just sitting there stationary, and you start running towards it. When you start running towards it, the frequency is going to appear higher to you, or have a higher pitch. And what's actually happening is the wavelength is now shorter. Okay. The other thing could happen, like, I don't know if any of you guys ever stood on the side of the street and had like an ambulance or a fire truck or a police car like fly by you, and as the police car approaches, the siren actually appears to have a higher pitch, and as it approaches, it gets higher and higher and higher, and then as it passes you, the pitch gets lower and lower and lower. And that's actually the second thing. Once the object starts moving away, or the sound source starts moving away, the frequency is lower and there's a longer wavelength. The faster the object moves, the more shifting that actually would occur. Right? Another example of this would be if you've ever listened to a like NASCAR race. As the cars fly by, you can hear that change in pitch as the car passes the fans in the stand, or for my case, if I watch it at home, it'd be the camera that's taping the race. So this, again, a picture might kind of help. When a sound is made by a stationary object, you hear a certain frequency, okay? And it would look something like this. Okay, here's the object right here. Okay, I'll make this really big. And let's say it's, making one, like screaming one tone, if you will. Okay, the sound waves spread out in a 360-degree area, and you'll notice the distance between these wave fronts is the same everywhere. Okay, and the reason why is because this object isn't moving. Okay, now let's say this guy or gal is screaming and decides to start to run. Okay, while they scream. Okay. Well, what it would look like is if this person, which is standing right here, is running this direction, you'll notice these waves get compressed at the front and stretched at the back. Okay, so if you were, say, standing right here, okay, as this person's running by you screaming for whatever reason, maybe they saw Bigfoot. Okay, they're running by screaming, these waves would be compressed and it would appear to have a higher frequency than he or she really would be screaming, if that makes sense. So the waves are getting compressed, your ears are sensing that compression, and so it sounds higher pitched than it would. Well, let's say now that this person has moved and you're standing here. As you stand here and as this person runs by you, you'd be starting to get into this area. And basically the waves are getting stretched because as this person runs away from the supposed spotting of Bigfoot, the waves are starting to being stretched, and so the frequency would appear lower, the pitch would sound lower, and there's also a bigger wavelength. You'll notice the distance from here to there, that's called a wavelength, is much larger than, say, the distance from here to there, which is another wavelength. Okay, and that's the Doppler effect. This person here hasn't changed their frequency at all. They're still screaming at the same tone or pitch, if you will, but basically because of their movement, that's causing observers to sense a different sound frequency. If an object moves at the speed of sound, you get something called a sonic boom. Okay, and basically what's happening is these wave fronts are overlapping one another. Okay, and you get something called a sonic boom. What's really kind of interesting to think about is if you travel faster than the speed of sound, which is very much so possible to do, you actually are gone before the boom is heard, which would be really weird. You're sitting in the plane and you're creating a sonic boom, but you don't even hear it because you're moving faster than you could actually pick up that sound. Okay, you're gone before it happens. So let's take a look at a Doppler effect problem. It says a car's horn produces a sound wave of constant frequency. Okay, so a car is laying on their horn and it's producing this constant frequency. As the car speeds up, going away from a stationary spectator, the sound wave detected by the spectator will do one of the following. Okay, so just real quickly a picture here, and again, my art skills are not great, but this is supposed to be the car, okay, and it's moving, all right, and it's moving this direction. And you're standing here, just not moving at all, listening to this car's horn. We'll make that be the car's horn, okay? This person here, what are they going to notice about that sound source? A decrease in amplitude and a decrease in frequency, a decrease in amplitude and an increase in frequency, an increase in amplitude and a decrease in frequency, or an increase in amplitude and an increase in frequency. Now, this isn't something I talked about in this lesson, but if you remember, amplitude is referring to the amount of energy the wave transmits. So a high energy wave is going to have a higher amplitude, which means basically a louder sound. Okay, amplitude is related to loudness. All right, so if a car is moving away from you, I think we all can assume that the loudness would decrease. So a decrease in amplitude is very possible. So right now I'm looking either 1 or 2. Now the second piece of this is what we just learned about this thing called the Doppler shift. As this car moves away, the wavelengths behind the car are going to get stretched. And so there's actually going to be a decrease in frequency. The wavelengths are going to get stretched, and so it's going to sound lower. And so 1 would be our answer, a decrease in amplitude and a decrease in frequency. Let's just take a look at another problem. A car's horn is producing a sound wave having a constant frequency of 350 hertz. If the car moves towards a stationary observer at a constant speed, the frequency of the car's horn detected by this observer may be one of these options. Okay, so again, let's just quickly draw a picture just so you can kind of that's supposed to be a car. Kind of get an idea of what's going on here. This car's moving this direction, honking his horn because you're like in the road or whatever. You know, I don't know. You're crazy. You're staying in front of a car. All right. You hear this car. Let me back up. This car is producing a frequency of 350 hertz. What are you going to observe here? Because the car is approaching you, the frequency is going to be higher than what the car is producing. So we're going to be looking for an answer higher than 350 hertz. And if we go through this list, the only answer that would fit that bill is this one right here. It's possible that would be maybe 380 hertz. So those are the type of Doppler shift problems I could give you. Basically, it's just conceptual. You won't need to do anything mathematically. So hopefully that wasn't too bad. We can do a little more practice if we need to in class. That should take care of this video. I will see you guys next time.